Hi everyone, my name is Nick Schuler and today I will be discussing a paper written by Ivins et al. In 2007 titled Post-Glacial Sediment Load in Subsidence in Coastal Louisiana, as well as to describe a simple 2D flexural model, which was my best attempt to recreate the results in this paper. Starting with a brief introduction about the problem and situation presented in the paper, we first have to understand the complexity of what occurs in coastal Louisiana as far as loading goes. Although the Louisiana coast is far removed from former ice sheet centers, the retreat of the Laurentide ice sheet following the last glacial maximum produced widespread solid earth deformation during and after this ice sheet demise. Recent glacial isostatic adjustment models show that the peripheral bulge has now migrated over 1,000 kilometers north from the Gulf Coast, and the regional residual vertical motions are small at present-day rates. However, sediment transport deposition and loading at the Gulf affect present-day vertical crustal motion in higher magnitudes. In this paper, they modeled both the sediment and ocean load to test predictions of subsidence to that measured using GPS data. Since ocean loading didn't produce as much of a response as sediment loading, for my model and most of the paper, they focus on sediment loading and the deflection created by it. A basic characteristic of regional Holocene sedimentation is delta switching, a systematic diversion of sediment associated with fundamental shifts in the course of the river. Switching occurs every 1 to 2,000 years, and the simulated Holocene is guided by the switching history, modern rates of deposition, and lobe thickness. Due to all the complexity, the easiest and most reasonable flexural model for this situation, in my opinion, is a 2D model that best represents an elastic lithosphere with an end load. This end load being sediment deposition to coastal Louisiana. The top figure on the right is from Yule et al. In 2009. It just simply shows in a basic schematic what is going on as these sediments are being deposited in coastal Louisiana. The bottom figure is a grid of the ocean loading magnitudes across the Gulf Coast. The dark blue line represents vertical motion of 0 millimeters per year with a contour interval of 0.1 millimeters per year. So these are very small rates. They list the viscosity and lithospheric thickness here, and we will go over the importance of that later on. Moving on to the simple 2D flexure model that I created to try and replicate their results. The goal of this model was to use parameters mentioned in this paper, slightly change some of the inputs, and see if I could reproduce a similar shape in subsidence rates comparable to coastal Louisiana over the course of a year. The equation I use can be seen below the plot, which represents the deflection of the elastic lithosphere under an end load. Coastal Louisiana is represented by the left side of the plot, where an end load is creating about 7 to 8 millimeters of vertical displacement. Northern Louisiana is on the right side of the plot and has reached equilibrium and isostatically adjusted to the end load. Notice the middle plot where a little peripheral bulge is created. This uplift in the lithosphere is due to this end load and represents real-life situations by the Sabine uplift in areas just north of Baton Rouge. The figure on the right is a grid representing the vertical motion rates due to sediment loading. Notice how these are much higher in magnitude, 1 to 8 millimeters per year. Also notice the area just north of the zero line, around Baton Rouge. Here they are seeing close to 1 millimeter per year of uplift, which we can also see in our peripheral bulge in the 2D model. Finally, we will go over some of the conclusions determined in this paper. The forward model and its parameters assuming incompressible elastic lithosphere on a Maxwell viscoelastic half-space, or mantle, is in reasonable agreement with GPS measurements, giving them confidence that their work is accurate and represents real-life coastal Louisiana as best as possible. While this was not one of the parameters I played with in the 2D model, they put extreme importance on the lateral variability in the viscosity of the mantle. That is a parameter that changed quite a bit for them, and they used lake cuts and studies for some comparisons and understanding. Now, we might have gone through this little presentation and think, why do we care? Well, the viscoelastic model has important implications for land use planning, as the predicted motions are sustained over 100 to 1,000 year timescales, so subsidence rates due to sediment loading are now quantifiable in future years. If you have any questions, please feel free to ask. Thank you guys for listening to my talk today.